All right, when last we met, we had been talking about dynamic memory allocation. And in particular, we had started talking about some of the things that can go wrong. We had talked about some of the common dynamic memory allocation bugs that you might encounter and wanted to kind of raise awareness of them so that you don't put them in your code. So here's one of them that we were talking about at the very end. In fact, this snippet of code has two separate bugs. And both of them are related to calling free on a pointer that you got back from, in this case, calloc, and then doing something with that pointer. So both of these statements here, where in the first one you're accessing through that pointer that you've already freed, and in the second one you're trying to call free on that same pointer again, both of these are bugs. So the first one is problematic because you are storing through that pointer. You are storing something into some location in memory. And that location in memory you have now already declared you're not using for this purpose anymore. So a couple of things might happen. One is free might have actually given this memory back to the operating system. The operating system might have marked it as not in use by your program anymore. And in fact, if you now try to access that memory, say store something there, or even read that memory, the operating system could say, you don't get to do that, and crash your program. This is known as a segmentation fault. The other thing that might happen is that somewhere in between this free up here and the use of that pointer again, you might have called malloc or calloc, or one of the allocation routines, to allocate memory in a completely different part of the program. And now this is more insidious, because now the store through the variable, some ints, will succeed. It will go ahead and put the value x in memory, but that memory you're now using for something else. And the symptom here will be that this code, this store, will work perfectly, but some completely different part of your program will suddenly find a value that where did it come from? It came from Neverland. And like I said, this is actually more insidious, because this is the one that will leave you up until 3 a.m. trying to debug what's going wrong. And so we have a suggestion for this, which is after you free some pointer, you go ahead and set that pointer to null. So now what's going to happen is that if you do this next line, you try to store through that pointer, you're now dereferencing the null pointer, and that you never get to do. At that point, your program will crash. You will get that segmentation fault. And now at least you'll know, hey, there's a bug here. I need to find it. And usually this will be reasonably easy to find, especially if you use a good debugger. And you can figure out which pointer is now null and you're still trying to go through it. Okay, so invisible bugs, bugs that don't make themselves apparent, are worse than bugs that crash your program. That is one of the general principles we want you to sort of internally absorb. Debugging is hard enough as it is. We will spend an entire lecture on debugging techniques. But one of the basic things is know that you have a bug and try to know as soon as you have the bug, instead of having it show up in some very indirect way somewhere else. All right. One more memory management bug, this one with realloc. And this is, a little variant of the bug we looked at 2 bugs ago, where you call one of the allocation functions but don't check its result. So what is the bad thing that can happen here? Well, you call realloc, you use the same pointer to it, everything is good, but if the realloc fails, not only is sumInt set to null right now, because realloc failed, but in fact it's a little bit worse, because now the part that you allocated through this original calloc did not magically get deallocated. If realloc fails, it does not free the old memory. And so now you have two problems. sumInt is set to null, which you didn't check for. And number two, the memory you did allocate, you're never going to be able to free again because you no longer have a pointer to it. So two separate bugs. The second one is called a memory leak. In general, whenever you allocate memory but don't end up freeing it, that is known as a memory leak. All right, so here is another version of the same bug. People sometimes, just call realloc and don't even try to grab a pointer to the resulting memory. So now, even if realloc succeeds, realloc may have reallocated your memory. It may have copied the values that you had in sumInts into some different location in memory, but now you're not grabbing the return value of realloc, and so now realloc did its job, but you don't get to access the new memory that it allocated. Okay, any questions on these last two bugs? What does it mean that there's an eventual double free? So double free is calling free on the same memory twice. So if realloc succeeds, it has already freed the original memory. But now you're going to try to access through that pointer to that original memory, call free on that pointer because you didn't save the return value of realloc, and now you're going to call free on the same pointer twice, and things are going to go horribly wrong. Are you starting to appreciate the way that Java works now? Where Java doesn't require you to explicitly call free on things, it uses a technique called garbage collection, where periodically it goes through memory and tries to figure out, are there bits of memory that you have allocated, but you no longer have a pointer to? And if it finds those, it automatically frees them. So there's a efficiency versus safety trade-off here, or perhaps efficiency versus convenience trade-off here. Java is a lot safer, and it's a lot more convenient to use. C, which is an older language, but also a lower level language intended to be, very efficient, requires you to do all of your own memory management. And like I said, way back when, this is a big part of why we want you to learn C. We want you to learn this other strategy that some programming languages take, so that you really see what is going on, with memory management, instead of having it done for you behind the scenes. All right, let us ask a little question. What's the bug? Simple enough. All right, we have a grand total of 4 people who answered A. Yay. 1 person who answered C. 2 people now who answered C. Yeah, somebody, anybody. What's the bug? What do you think is what do you think is wrong here? Yes. Ding, 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 ding. Yes, absolutely. This is one of the most common bugs. Please don't make it. I know you will, but please don't. Stringlen does not count the terminating null character. So you didn't allocate enough memory in the new copy. You were off by one whole byte. And, you know, this is one of these things that 9 times out of 10, you know, you actually won't see a bug. And that 10th time, the program will crash. So again, this is one of these things that is dangerous because it doesn't always crash. And that's why we want to call your attention to it. Right? So the problem is allocates 1 byte too few. All right, let us look at something else. What about this one? You notice we're not making that previous bug because we're doing string length plus 1. Nice, 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 nice. All right, somebody who said C. Why do you think this is wrong? Yes, up in the orange. Or are you? No, not ready to answer. Somebody who thinks this is wrong. Why is this wrong? Yes. Absolutely. malloc can absolutely fail. And when it does so, it returns null. And now suddenly you are trying to string copy something into the null pointer, and bad things will ensue. All right. So that is that for dynamic memory allocation. Any last questions before we move on to testing? All right. All right, so the remainder of today we're going to spend talking about testing programs. Interesting little quote from Charles Babbage, the inventor of one of the very early mechanical computation engines, I guess he called it. I don't remember exactly. Anyway, one of the very early computers. Why test? Well, because code has bugs. Ideally, you would have some big general tool that takes as input a program, takes as input what the program is supposed to do, and tells you yes or no, the program is correct. Unfortunately, very clever guy, Mr. Alan Turing, got his PhD from Princeton, 1938. He actually wrote his thesis all about how you don't get to do this. It is just theoretically impossible to write a program that, makes conclusions, makes proofs about whether an arbitrary other program is correct, or even very, much simpler versions of this, such as, does that program enter an infinite loop? This is known as the halting problem. Okay, so scratch that off. Semi-ideally, we would semi-automatically prove that some programs are correct. So you could have a program that takes, again, another program and a specification with some user assistance, either is able to verify that that program is correct or no answer. So this actually is possible, but most people don't do it. It is horribly complicated and messy. And if you're interested in doing this, I suggest taking COS 326 and then going on to something like COS 510, where you learn all about program verification. We're not going to do that. What we're going to do instead is to talk about testing, which is kind of the practical version of what you do to convince yourself that your program might be right because you did a thorough job of testing and didn't find any bugs, or that your program is definitely wrong because you found a bug through your testing. And like I said, this is kind of what happens in the real world. If you go out and you get a job at a software company, believe me, you will spend a huge fraction of your time writing test cases. In many companies, you don't get to contribute to the code of a product unless you simultaneously contribute test cases. Like literally, you don't get to check the code in unless you have test cases that you're checking in. So you're going to spend a big chunk of your time testing code, and you want to be efficient. So today is all about what are some strategies for doing program testing. So you can break down different strategies for testing along various axes. One is who does the testing. One is if the programmer, the person who actually wrote the code, does the testing. This is known as white box testing. You know the code, so you can actually systematically go through and test all of the bits of the code, all of the paths that the code could take. On the other hand, you're the one who wrote the code in the first place, so if you made a bug writing the code, you're probably going to commit the same thinko when you are designing test cases for the code. You're biased by the code design. So this leads to a strategy called black box testing, where the code is tested by a completely separate set of programmers known as QA engineers. They are unbiased by the code design, so they can, think about this from the specification point of view and start developing test cases based on what the code is supposed to do, not what the code actually does. On the other hand, because they don't know the dirty little secrets buried in the code, they can't design test cases that sort of test all of those sketchy things that you wrote the code to do. In practice, big companies do both of those, plus there is field testing. So you create a version of the software known as a beta version. You give that to some trusted customers, and you tell them, test this in the field. And your customers, the people who actually use the code, are probably going to use the code in slightly different ways than the QA people, because they're the ones who, are able to debug, what they want the code to do, not what the code was specified to do, and not what the code was written to do. So the pros are that you get code being used in completely unexpected ways, but shipping code to your customers that you're not sure is correct or that you haven't tested very thoroughly is not something that they may like to do. So lots of different strategies. Today we're mostly talking about kind of this white box testing strategy, but we'll touch on some other things. All right, so external testing. This is testing the program kind of as a unit, testing the execution of the entire program. So we looked at this kind of upper one program many, many lectures ago. Let's say you wrote it, you think it might be correct. Now, how do we test it? Well, the first thing you do is, you run it on some sample inputs and, just basic sanity check. Okay, great. Fine to do that once. Maybe okay to do it twice. But if you're a programmer, and remember we encourage programmers to be lazy in the right ways, it's tedious to repeat the same tests every single time. And you want to repeat the tests over and over again as the program evolves, as you make changes to the program. So, the next level up is you start to systematically organize the tests. You create a bunch of files with sample inputs. You create a bunch of files with the correct output. And you repeatedly run the code on all of the inputs compared to the expected output. Okay, great. And now, to be even more lazy than that, you actually can list all of the tests that you want to execute, compile them into a shell script. This is basically a list of commands that the shell, that bash is going to execute, run right after the other. And now, with one command, namely execute this script with that shell, the shell executes everything that was in that file. And notice what it does. It runs the program on a particular input, saves the output, and then runs a command, CMP, to compare the actual output to the expected output. And so when you run this shell script, no news is good news, right? If it doesn't output anything, that means that all of the comparisons came out correct. But if any of the actual outputs disagreed with the correct outputs, then you know about it. So with one command, you can actually run a bunch of different tests against your code. And lo and behold, on assignment 1, we gave you a script that looks like this. It's called test decomment, right? You all remember running this. And this is what it looks like. It basically, says, here's how you use it. You just run test decomment. And then this for syntax is the syntax for a for loop in the shell. Kind of, a little bit different from for loops in C or Java, but accomplishes the same thing. And basically says, given all of the input files that end in .txt, I'm going to run a particular command on that input file. And so this, what it does here is test decomment diff, which itself basically, runs the program on that input, compares it to the expected output, and complains if there's a difference. And you could either have that piece be its own shell script or actually include that in the for loop. All right, so this is a good, very good general strategy. And the reason it's important to compile all of that into a single program is that you want to use it in a strategy known as regression testing. So regression, in this case, means that something regressed. Something that used to be correct is now no longer correct before. So regression testing is the strategy of every time you make a change to the code, run all of the tests that you have, and make sure that stuff that used to work hasn't been broken by the change that you just made. Because if you don't do this, you do this. You get into the situation that every time you make a change to the code, you introduce new bugs. Okay, so regression testing is very important just to make sure that you're making forward progress, not backwards. Make sure that you know, whenever you've made a change, that you are making forward progress. And there's another piece to this, which is whenever you find a new bug that wasn't caught by your previous regression tests, you create a new test case that tickles that particular bug, and you add it to your set of regression tests. So over time, what happens is your code, hopefully, gets more and more correct, and your test suite, hopefully, increases to exercise more and more of the code. Any questions on this strategy? All right, so what if, you're such a good programmer that you run your regression test, it's fine. Okay, are you done? Well, it could be that your code is perfect, yeah, right, or it could be that your test suite is imperfect. And so, at least early on in testing, one of the things you might want to do is test the test suite. And the way you do that is you intentionally introduce a bug in your code and make sure that whatever tests you have been running are powerful enough to catch that bug. So this is known as fault injection, where you deliberately put in a bug into your code temporarily, remember what you did, remember how to undo the bug, obviously, and make sure that you have enough test cases to catch that particular bug. And the more you do this, the more you gain confidence that your test suite is actually powerful enough to catch a large class of bugs. So is this the best way? So this is certainly a good component in your suite of testing strategies. But, there are some limitations to this. One is the program has to have one right answer. You have to know that one right answer. A lot of the time, programs are interactive. A lot of the time, the reason you're writing a program is because you're trying to compute something that you don't know the answer to. Plus, it requires having this large test suite. It requires keeping that test suite up to date as things change. So instead, there's another component in your suite of testing strategies that exploits modularity. So one of the big lessons of COS 217 is that if you want to write big programs, you're not going to be smart enough to understand the entire program at the same time. Nobody is. You just can't keep a million-line program in your head simultaneously. The only way you have a hope of understanding a large program is to think of it as a collection of smaller modules. And those smaller modules are a collection of smaller submodules until you get something that is this big, and yes, you can keep it in your mind at the same time, and you can understand what the algorithm is, what it's doing, how it's working, how it's broken. So writing big programs is best done by exploiting modularity, and testing big programs is also best done by exploiting modularity. So here we move into the realm of white box testing. where it's really you, the programmer, who knows the structure of the code, and in particular knows how you used modularity to write that code, you can use that information to help you design the testing. So one strategy is internal testing with assertions. When we say assertion, we mean a particular macro defined in the header file assert.h. And the macro is named assert, and the way you use it is in your code, you write assert and then some expression in parentheses. And what this is going to do is it's going to evaluate that expression. If the expression is true, in other words, non-zero, it's going to do nothing. But if it's false, it's going to complain at you and exit the program. So how do you use this? Well, a very simple way of using this is to validate parameters into your function. So let's say you're writing a greatest common divisor function, GCD. Well, one of the basic things is that you're probably going to write it to work only if the integers are positive. Unfortunately, the compiler can't read your comment. It can't read that you want those integers to be positive. So the way you express that in code is with these assert macros. So in fact, if you're using this function correctly, you pass in positive integers, the asserts go straight through, and the code gets executed. If you end up calling the function incorrectly, what happens is that one of the asserts will fail, and the program will stop right then and there. And if you're running the program in a debugger, you can then trace back and see where you called it from and so on. Similarly, at the end of the function, you can write down as many properties you can think of that the output should satisfy and check all of those properties. So what do we know about what GCD should return? Well, we know that it should return a positive value if we called it on positive inputs. We know that it can't return anything bigger than the inputs. So these are the asserts we have included here. Another very common thing you can assert is that array subscripts are valid. You're writing some function, you have some array that you're accessing. You can check whether array subscripts are in the range 0 to length -1 before you try to do an array access. Still, another thing you want to check is, certain common outputs of functions. For example, scanf. If you want to read two integers, maybe the user didn't type two integers, you want to check them. But wait a minute. We don't really want to use assert for this one. Here's the difference. In those previous cases, if we know that the code is correct, we might be able to remove the asserts or disable the asserts at compile time, and we'll see how to do that. And the code is still, correct. You have confidence it's going to work. On the other hand, this is not checking something relating to the code. This is checking something relating to the user of the code. And I'm sorry, you don't magically get to declare that the user of the code is correct, that the user isn't going to make a mistake. So in this situation, even though it looks like, similarly you're verifying function values and things like that, this is a very different situation, and it's not appropriate to use assert right here. Okay, on the other hand, here is a case where it is appropriate. It's things like checking invariance, again, within the code. So in this strategy, we write some little isValid function that takes as input some data structure, verifies that the data structure is sane, that it is structured correctly, that its contents are appropriate. And now periodically, whether it's at the beginning of a function, at the end of a function, in the middle of a function, we can call that checker to verify that your data structure is correct. And especially if you have a loop where you're doing a bunch of stuff manipulating this data structure, it can be very, very helpful to call this checker in the middle of that loop so that as soon as you break the data structure with your code, you know about it. And that's the big advantage of actually writing a separate function to do the checking. Because now with one line of code, you can just drop that line all over the place, and it becomes very easy to find where you are mangling your data structure. This becomes especially important if your data structure involves a bunch of pointers. Because once you have mangled it beyond recognition with pointers pointing who knows where, it can be very difficult to see how that happened. So check your data structures along the way with a checker function and an assert. Questions here? All right, next testing strategy is called unit testing. So this is all about testing modular programs, such as assignment 2, hint, hint. So let's look at what a modular program might look like. So there's a header file for some little module in the code. And there is an implementation file. And there might be other implementation files, or there might be other files that use the module that you just wrote as a submodule. So in assignment 2, you have string manipulation functions, and the collection of those is its own module. And then there's another module, which is actually using those string manipulation functions to implement search and replace. So unit testing is all about testing modules separately. So let's say that you have some module embedded in your program that you care about testing really, really thoroughly. Let's say that it's this function 2 thing. Now, in a large program, things get a little complicated because that module might depend on certain submodules, and during coding, you may not have written those submodules yet. Similarly, that module may be called by some other code that you haven't written yet. So the idea of unit testing is to try to isolate a single module, and you write a little tiny bit of support code. The support code is a scaffold, sometimes called a testing scaffold, which is code that calls the module and tests it in particular ways. And the submodules, if you haven't implemented those yet and you haven't tested those yet, you can replace them with what is called stub code. So maybe the stub code doesn't work in all of its generality. Maybe it's a very simple version of the implementation, but it's sort of just enough to make the module that you care about work in the situations that you want to test. So you're isolating a single module and writing temporary, super simple versions of everything above it and everything below it and everything around it. You're creating this testing environment for this particular module. Okay, so if you want to test the string manipulation module for assignment 2, well, you could write some code that will systematically go through and test all of your string manipulation functions. So for example, if you want to test the string getLength, here you, create the inputs instead of relying on, the rest of the program to create those inputs for you. So that, you can think of these temporary variables, the source variables, as being sort of the scaffold that you're creating. Then you call the module that you're working on, and then you test its return values. And this you might as well do with an assert. Okay. So you can write these types of testing functions for all of the different string manipulation functions, and we kind of want you to do that. A good way of being confident that your implementations are correct. Okay, questions here? All right, let's talk a little bit about test coverage. There are two primary ways that you can think of test coverage. And by coverage, I mean making sure that you test all of the code that you wrote. The most basic one is called statement testing, which is, basically testing enough that you're confident that every statement in the code got executed. So let's say you have a, piece of code that looks like this. If you're doing statement testing, you should make sure that you do enough testing that you test both if statements, that you test statement 1, statement 2, statement 3, statement 4, all of the things within the if-else. Okay, so let's ask this question. If we have code that looks like this, and you want to do statement testing, how many test cases do you need? Kind of in an ideal case. All right, so this is a pretty simple one. Obviously, you need kind of two statements here. One that might, be true for condition 1 and condition 2, and another one that results in both of those if statements going false. And at this point, you're kind of sitting here wondering, well, yeah, obviously, why are we talking about this? And the reason is that there's another way that you can think about coverage, which is actually path testing. So here, you want to execute not just every statement, but every possible path through the code. And so if we look at the same code, we can also ask, how many test cases are you going to need in order to get full path coverage through the code? And the answer turns out to be different. Right, so most people get that you now need 4 different test cases because there are now 4 paths through the code. And if these statement 1, statement 2, statement 3, statement 4 are not completely independent of each other, if, let's say, statement 1 does something that's then going to affect whether statement 3 or statement 4 might be correct, you can see how path testing might be a more complete way of testing the code and making sure that interactions between different parts of the code are correct. So now here's the bad news. In a complicated program, you get kind of this exponential explosion, right? Every if statement is going to multiply the number of paths by 2. Well, unless the conditions are set up such that, they really are mutually exclusive. Every switch statement is going to multiply the number of paths by some huge number, basically the number of cases in the switch. can really see how this quickly becomes unmanageable. For complex programs, we would like to be able to do path testing, but in reality, we sort of accept that we can't, because the number of paths through the code just gets too large. So as you're designing test cases, certainly think of statement testing as a good goal to shoot for. In really simple cases where you see that there are going to be interactions, try to do a limited form of path testing to at least try to hit those interactions and make sure your code is handling those correct. Another way of designing tests is to think about boundaries or corner cases. So use values just below or just above the limits of an input domain, and values causing outputs to be at, just below, and just above the limits of an output domain. Okay, so how would you boundary test a function that looks like this? So read what the function is supposed to do. Think of what, in your mind, are the corner cases, the boundary cases. And now think of test cases. How would you test code that looks like this? Well, here are some examples you may have thought of. So you create some, a test harness, a test scaffold, create an array, assign some values within the array, and now repeatedly call this find function. So if you want to find the first value in the array, make sure that that works. If you want to find the last value in the array, make sure that that works. If you want to find a non-existent value in the array that happens to be in memory right after the valid part of the array. So notice here we're calling it with a length of 9. So this last value in the array A is not part of the valid region that we're passing to find. And we want to make sure that find fails in that case. If we're looking for the first value in the array, but we pass in an array that starts past that, we want to make sure we don't find that. So think of a lot of boundary cases like this, and this can be a very, very important strategy for you. And now we come to the exact opposite. Instead of being smart about how you generate test cases, another strategy is to be dumb about how you generate test cases. Automatically generate a bunch of data. Random data. As random as you can make it. As big as you can make it. Make sure your code still handles it. Make sure it handles big data sets, textual data sets, non-textual data sets, binary data sets, random data sets. So stress testing. Make sure that your code deals with unexpected inputs. And the best way to do that is, you as the programmer shouldn't be the one generating those inputs. Think of programs that generate inputs for stress testing. Yeah? In a lot of cases, they would. And sometimes you can't actually check the output. And this is much more about checking the input. Sometimes you can test various properties of the output that aren't a complete check on whether the output is correct. So a lot of ways that you can deal with that. Question here. So why don't we take it offline? Why don't we take it?